In this video, we're going to take a look at our cosmic address. We'll start at Mount SAC as if we were actually having class there. The two pictures I've shown here, the one on the lower right is a picture of the planetarium during one of the shows, and the picture in the upper left is the top of the astronomy building showing one of the astronomy domes right here. So there's a telescope inside of here, and one of these side buildings holds a few other portable telescopes. So if we were to write a letter and put our return address on it, we would start with our names and then Mount SAC. Next, we'd add the city of Walnut, in which Mount SAC is inside of. And then after that, of course, we would have the state of California. So if we keep zooming out to larger and larger regions, they're taking up much more space, but they're also incorporating all of the other bits inside of them, meaning that California has many, many, many different cities, of which Walnut is just one of them. And many of those cities will have colleges and universities and other schools of their own. So as we zoom further out, not only do we see larger numbers of the smaller pieces inside of them, we're also taking up a larger region of space. Now, if we think about the state of California, we can't see it in this map. There are lots of cities in the state of California, and there's also lots of empty regions within those cities. So we'll start to look at how we divvy things up as we move further out. So moving further out, one step larger than the state of California is the United States of America. If we zoom out further than that, I'm not going to get into continents, although we could do the continent of North America, of which the United States of America is a substantial part. But if we zoom further out than that, then we're at Earth. This is one of my favorite pictures of Earth taken by some of the Apollo astronauts on the way to the moon. And in this picture, we can see here's the continent of Africa, here's the Middle East, and Antarctica is down here in the bottom. So the blue is where the water is. There's Madagascar, the island off the coast of Africa. White through here, this is all clouds. And you can start to see some other islands and whatnot around here. So if we zoom further out from Earth, we get to our solar system. Now this picture of our solar system is known as a composite, meaning there are actual images of the planets and the sun in this image, but they've been pasted together like in Photoshop. So the planets are in no way that close to each other. They're in no way that close to the sun. We would all be dead and burned up if we were. And they're definitely not all in a line. So we'll look at how planets move throughout the solar system as we move forward in this class. But this does give us the relative sizes of the planets compared to each other and to the sun. So the sun is so large compared to the planets on this scale, I can't even fit it all on my screen. And we can follow through the planets in order from here. So Mercury is very, very tiny. Venus is next. Venus and Earth are about the same size. We're not showing the Earth's moon here, but it would be orbiting the Earth. Mars is next. You can see Mars is smaller than Earth. And then in here, which we're not showing all of them because we're just showing relative sizes of the major objects, is where the asteroid belt is located. Ceres is the largest asteroid in the asteroid belt, so it's shown there for comparison. Now this particular figure is showing the main planets here. So we can count 1, 2, 3, 4, 5, 6, 7, 8. Not the 9, depending on when you grew up. The 9th, of course, was Pluto. But we have now found so many different planets that are much, much smaller than Pluto even, that we've created a new designation. And we'll talk about this a little bit more when we get into our solar system. So the demotion of Pluto happened before with Ceres. When Ceres was first discovered, it was considered to be a planet. And then we found that there are millions of other objects just like Ceres in the asteroid belt. So Ceres was demoted to just an asteroid. That's essentially what has now happened with Pluto. There are millions of other objects, some larger, some smaller than Pluto, in what's now known as the Kuiper Belt. And this 2003 UB313 is another example of it. That's its original discovery name, and it's been given a proper name now, as well as a number of other objects in the Kuiper Belt. So these have been called dwarf planets. So they're very, very tiny, but they're still being able to hold themselves together under their own gravity. So The largest planets here are sometimes known as the gas planets or the ice planets. They're much larger than the inner planets here, primarily because of where they're located, the fact they're located in the outer solar system. And as I said, we'll talk about this a little bit more as we move through and talk more about the solar system. So here we'll focus on our cosmic address. So this shows the major objects in our solar system. Now, our solar system, the sun and the planets and all of the other objects that orbit the sun, are just one tiny star in our Milky Way galaxy. So this is a drawing of what we think our Milky Way galaxy looks like. Because we're inside of it, we can't take pictures of it. Just like if you were on Mount SAC's campus, you wouldn't be able to get a nice aerial view of Mount SAC. You'd have to use a drone or get in an airplane or a helicopter and get above Mount SAC to get that nice aerial view. But if you look around, you can still get a rough idea of where different buildings are, and you could probably make a map for your friend to be able to get them around. That's essentially what we do in trying to determine what our galaxy looks like. So our Milky Way galaxy is a barred galaxy. There's a bar that goes through here. This is the center. We'll learn more about the parts of galaxies as we move along in the term. These are the spiral arms. Our sun is about 2/3 of the way out from the center of the galaxy in one of these spiral arms. Now, our galaxy is one of just many billions of galaxies in the universe, but close to us, we have what's called the local group. So a small collection of galaxies that sort of orbit around each other. So this is us, the Milky Way. We have many satellite galaxies, very tiny galaxies that orbit our Milky Way. The largest of two are these two right here, the Small Magellanic Cloud and the Large Magellanic Cloud, named after Magellan for being the first white European to observe them, since you have to go into the southern hemisphere to be able to see them. Now, there are other galaxies around here as well. The next largest is this one right here. So this is known as the Andromeda Galaxy. It's larger than the Milky Way, but together the Andromeda Galaxy and the Milky Way Galaxy make up the two largest galaxies in our local group. The others are much smaller compared to us. And along in this image, you can see just how far away from each other they are in kilometers. I start running out of names to describe how large those numbers are, which is why we'll start to see scientific notation as we move further along. Now, our local group is now this tiny little spot inside of here, is just one group in what, or cluster, in what is called the local supercluster, which is all of these things in here. So our local group is relatively small. This is the Virgo cluster. You can see it's much larger. Every dot in this simulation corresponds to a galaxy. So the Virgo cluster is a group of galaxies that has many more than our local group, which is why we actually call it a cluster. So the difference between the name group and cluster correspond to how many galaxies you have, how compact, how close together they are. So you can see these are called groups because they have fewer galaxies in them, whereas these are much denser, so they're clusters. So this collection of all of these groups and clusters is known as our local supercluster, although sometimes some people call it the Virgo supercluster, named after the Virgo cluster, which is the largest cluster of galaxies in our local area. And all of this is just empty space. Wherever you don't see a dot is a whole lot of empty space. So we can compare this back to our state, where we've got maybe the Bay Area and Southern California and a lot of empty space, even though there's still towns and cities all throughout there. If we zoom further out from the local supercluster, we're essentially looking at the universe in its entirety. This is one of my favorite images. So this image was taken with the Hubble Space Telescope. The director of the Hubble Space Telescope at the time told the operators to stare at what they thought was a completely blank piece of sky, and they stared at it for days. And when they finally went and looked at the image that they had, which they thought was a completely blank, empty spot of sky, this is what they saw. So we'll learn more about telescopes and light and how telescopes collect light over as we move through the term. But we can start to see that there are so many galaxies out in the universe. The current estimate is somewhere around 50 to 100 billion galaxies in the universe. Every point of light you see in here is a galaxy, even these little teeny tiny ones that you can barely see, which just is one of the reasons why I love, because there's just so much out there to learn about. We don't have enough people nor enough time to be able to figure out it all. So here's an overview of what we just started. So if we start with Earth, again, here's the African continent. Then we can start to look at, zoom out, and we see our solar system, and they've zoomed out some of the other planets there for you to be able to see them. So it takes light, the amount of time it takes light to travel from the sun to the Earth is 8 minutes, to give you a rough idea of scale. So we often use the amount of time it takes light to travel a specific distance as a measure of how far away things are. So we could say that the distance between the Earth and the sun is 8 light minutes, because it takes light 8 minutes to get to us. Now it takes light 5.5 hours to get from the sun to Pluto. So that would be 5.5 light hours would be the distance from the sun to Pluto. And to the nearest star, which we don't really have shown in this overview, but from our sun to the nearest star is 4.3 years. That's how long it would take light to travel there. So the distance we say is then 4.3 light years. It's 100,000 years for light to travel across the Milky Way galaxy here, and 2.9 million years for light to travel from the Milky Way to the Andromeda galaxy. So that's between these two. 2.9 million years. And then it's about 10 billion years for light to travel from one side of the universe to the other, to the distant galaxies that we can see. The one side of the universe, I misspoke. From one side of the universe to the other side of the universe that we can see would be something around 30 billion years. But for the most distant galaxies that we're able to see, it's something more like 10 billion years for light to travel from us to those distant galaxies, or vice versa. So that's a little bit about our cosmic address and just how far away these things are from each other.